So the first question in relation to rates of change applications. Suppose the function be of 50,000 plus, and it represents the value in dollars of a new car T years after it is purchased. So this equation is describing this particular scenario. Mr. Bullock, can you just check if you can hear me? I want to make sure that I'm not muted on. Okay, perfect. So the question that we're being given, what is the rate of change of the value of the car at 2 years, 5 years, and 7 years? Now, this is just an example of how we can use the derivative to solve this question. Remember that your test next Friday will cover some application type questions. So the first thing we are going to do, rates of change always correspond to the slope of the tangent line, which is also the same concept as derivative. Now, in the functions course, we kind of explored the slope of the secant line as well as the slope of the tangent line. In this course, we're just focusing on the slope of the tangent line. So we are obviously using the quotient rule to solve this question. Now, because 50,000 is a constant, I'm going to basically, the slope of 50,000 plus 6t is simply only 6. And I multiply that by the bottom function, 1 plus 0.4t. And the quotient rule is always a difference in the numerator. So minus the derivative of the bottom function, 0.4, times the original 50,000 plus 6t. So I'm just going to exit full screen mode for a second so I can get my highlighter out. There we go. So the next step, I go back to full screen mode, is going to simply be to apply my distributive property. So I'm going to be multiplying my 6. Let's lock that in place. Okay, highlighter doesn't want to work in this mode. My 6, I'm going to multiply everything by my first set of brackets, and negative 0.4, I'm going to multiply everything with my second set of brackets and get a full numerator. Angelo has entered class, Mr. Bullock. So that gives me my full numerator. And my denominator is staying as 1 plus 0.4t to the power of 2. Notice we didn't use chain rule for this particular example. So this is just rates of change applications. When I simplify my numerator, the positive 2.4t eliminates with the negative 2.4t. So I get an actual number in my numerator, and that number cannot be reduced with my denominator. But because the question asked me to find the value of the car at 2 years, 5 years, and 7 years, with this derivative formula, I can find when t is equal to 2 years by plugging it straight into the equation to get a value in dollars per year. So it's decreasing by $6,170.99 after 2 years. If I plug in t is equal to 5, I get another value. So remember, this is per year. It's depreciating per year. And after 7 years. So you notice the newer the car is, the faster the rate of change, the depreciation is at the beginning, and then it starts to taper off, level off the more years that pass. Now remember, we were never given the initial value of the car. We were given a function to represent the value of the car in dollars. But if we are being asked to find the initial value of the car, does anyone have any idea of what value of t would we substitute into the equation to find the initial value of the car? Anyone? Yes, Carl. Yes, perfect. T is equal to 0. Before you drive off that lot, what is the value of the car? T is equal to 0 into not the derivative function, but the original function that we were given. So this is what application questions really measure, and you are going to see this in optimization. Do you know what each formula represents? So you know what formula to use for particular questions. If you use the derivative formula here, then that's a clear indication you're not understanding that the derivative represents the rate of change of the car, but the value of the car is the original function. Okay, so I'm going to move on to the next type of question. Okay, so we have a science question here. I'm going to move this out of the way. So kinetic energy is the energy due to motion when an object is moving. Its kinetic energy is determined by the formula kV is equal to 0.5 mv squared, where K is in joules, m is the mass of the object in kilograms, and v is the velocity of the object in meters per second. So when we get to our module 4, I believe, in optimization, you're going to see that we're dealing with lots of shapes and geometric objects. But optimization, I will be giving a lesson that you're not going to be tested on when we get there, that relates these concepts to physics and a lot of careers or subjects in the science area post-secondary, just to give you a connection so you can see where derivatives and the role derivatives play later on in your education. So the question is asking, suppose a ball with a mass of 0.35 kilograms is thrown vertically upward with an initial velocity of 40 meters per second. So we have a velocity formula where t is in time, t is the time in seconds, and we have a different formula for kinetic energy. So that's interesting. We have two formulas here. I'm just going to highlight those quickly. So the first question, express the kinetic energy of the ball as a function of time. So this is interesting. If we want to express kinetic energy as a function of time, we're going to actually substitute into the formula the mass that we know into m, 0.5, but we have a equation for the velocity. Velocity is equal to 40 minus 9.8. So into the original equation was 0.5 times mass times v squared. So you have to really remember to take your velocity formula and remember to square it, v squared. So when we simplify the 0.5 times 0.35, we get 0.175 times 40 minus 9.8 t squared. Now, the terms in the brackets are algebraic, so, and there's no greatest common factor that we can take out to combine with the 0.175. So that is going to be our formula for the kinetic energy of the ball. Right? This was just, question was just relating to the formulas we were given in the equation. But for the next question, whenever you see the words rate of change, right? Rate of change, last quad would always trigger slope of the tangent, slope of the secant line, using formulas that were very similar to what you learned in grade 9 math. Now, this quad, rate of change, we're going to leave that concept behind, and we're going to trigger every time you see the words rate of change, you can use this and relate this to derivatives. The derivative, the slope of the tangent line. Now that kind of puts students who are taking calculus right now and functions at an advantage, because when you do your test for your functions course at the end of this quad, you can actually use derivatives to check your answers for the concept that you're going to learn in your functions course. Okay, so just so you're aware of that. So the first thing I'm going to do is I have my formula for kinetic energy, because we're determining the rate of change of kinetic energy. But we also know that our original formula was 0.5 times m times v squared. We've solved that already. Let's see. Okay, so basically, actually, we're taking the derivative of this kinetic energy formula that we simplified up here. So what's happening is I'm bringing down the 2, multiplying that by 0.175. 40 minus 98t to the power of 2. When I subtract 1 from that, I get 40 minus 9.8t to the power of 1. Now, if you leave it like that, you are not completing your derivative, because you have to remember to take the derivative of the inside. That relates to the chain rule. So the derivative of the inside is 9.8, negative 9.8. So we have to remember to include that. I'm going to put a box around that particular component, which is the derivative of the inside function. And now when we simplify the negative 9.8 multiplied by 2 times 0.175, if we connect all the constant numbers, we have a simplified version of the derivative formula. Now remember, the question was asking us to determine the rate of change of the kinetic energy of the ball at 3 seconds. So I'm just simply going to plug in 3 wherever I see t into the formula. And that gives me a value of negative 36.358. Well, how do I convert this in numerical value into something that makes sense for a science question? With a statement. At 3 seconds, the rate of change of kinetic energy of the ball is decreasing by 36.358 joules per second. Now, if we didn't have this quad semester situation and we had more time, we would really be giving a ton of lessons about the importance for the statement, the interpretation of your numerical value. Because of the nature that we have now, Mr. Bullock, right? I think it's best that if you have the equation correct, that's fine. The written statement doesn't have to be, we're not going to be really focusing on the interpretation that you're saying that the ball is decreasing by 36.358. Simply don't have enough time to spend on giving you the proper insight and practice to be able to turn these numbers into statements. But please be aware that that is something that is very important for your first year courses. So when you are doing your homework, always try to consider the interpretation that is in your answer keys at the back of the textbook to make sense of the numbers. We're not going to be asking you to do any written statements on the test. The equations and the calculations will be fine for this year. Okay, so that brings me to example number 3. But example number 3 requires us to just have a little bit of clarification on the concept of linear diversity. So linear diversity of an object, here we put on our science hats, refers to the mass of an object per unit length. Suppose the function gives the mass in kilograms of the first x meters of an object. For the part of the object that lies between x1 and x2, the average linear density has this slope formula, and the corresponding derivative function is the linear diversity. So this is just relating the rate of change of the derivative back to, you'll remember this formula right here from your functions course and just from grade 9 in general, where you're using the points of a function to find the slope. That's the same thing as m is equal to y2 minus y1 over x2 minus x1. The slope formula you learned in grade 9. For those of you who didn't take functions already, when you are working with rate of change in the functions course, you're always referring to the slope formula. Here we're going to use the derivative to solve. So the mass in kilograms of the first x meters of wire can be modeled by this function, radical function. F of x is equal to the square root of 3x plus 1. Determine the average linear density of the part of the wire from x is equal to 5 to x is equal to 8. Now, because this particular question gives us 2 points, this is more of like a functions question, maybe relating the whole concept of rates of change back to the functions course, where we're simply going to find the corresponding y values for each of these points instead of using the derivative formula. And then we're going to compare the answers that we get when we use the derivative formula versus when we use our slope calculation. So how I would do that is the average linear density is equal to f of 8. That is the same as what is x equal to, the y value when x is equal to 8 of the function. And f of 5 in our numerator all over 8 minus 5. That's simply the slope formula. When we plug those values into the question and make sure to take the difference in my numerator and divide by 3 in the denominator, we get a value of 0.333 kilograms per meter. So just to make a connection between the functions and calculus course, let's see what type of answer we get when we start off with f of x is equal to 3x plus 1, and we write in our derivative. Oh, pretty interesting. The computer recognizes when the mouse is a highlighter and the stylus is a pen. I like that. Okay, so we're going to do the same question, determine the linear density at x is equal to 5 and x is equal to 8, but we're going to make an interpretation. What do these results tell us about the wire? So before I write my f prime of x, I'm going to write my f of x. So I'm going to rewrite f of x is equal to 3x plus 1 to the power of 1/2, power of 1/2. So when you take your derivative, I'm going to bring down this 1/2, and I have to remember to subtract 1 from the 1/2 in the numerator. That gives me negative 1/2. Now, I can't stop there according to the chain rule because I also have to take the derivative. That was taking the derivative of the outside of the function. I also have to take the derivative of the inside of the function, which is equal to 3. And once we get there, we can simplify. Now, when I highlight 3x plus 1 to the power of negative 1/2, that, because of that negative 1/2, that has to switch to the denominator. The 2 in the denominator of 1/2 also remains in the denominator. So the only thing that remains in the numerator is the 1 in the numerator of the fraction times the constant number 3. So 1 times 3 is obviously 3, which stays in the numerator. So here we have a simplified version of the slope of the tangent line, or our derivative formula. If I want to find the linear density at x is equal to 5 and x is equal to 3, all I have to do is simply substitute x is equal to 5, and sorry, not x is equal to 3, x is equal to 5 and x is equal to 8 into our derivative functions. And at x is equal to 5, I get a slope of 0.375. At x is equal to 8, I get a slope of 0.3. These are very similar to the average linear density that I got in part A, which was equal to 0.333. Okay, so the average linear density is a bit different from the slope of the derivative or the slope of the tangent line because that's an exact value. So because these linear densities are different, the material of which the wire is composed is non-homogeneous. So this is homogeneous, sorry. So this is something, remember, these interpretations are something we would do in a regular calculus course. In this compressed version of calculus, we are just going to be focusing on the equations and the calculations. Okay, so this next slide you just have to view. You don't have to write anything down. So this is kind of a cheat sheet we've required. We've provided of just often some, especially those of you who are interested in business, different ways where we use the derivative in business. So when we have a revenue function or a cost function or a profit function, every time you had financial mathematics in the last couple of years in MCR, MHF, or MCV, these are the type of functions we often focus on. We can do some very complicated things in the future in terms of derivatives. There's actually in the commerce program at many universities a required calculus course, which is called business calculus, that primarily focuses all of the applications on the marginal cost function, the marginal revenue function, and the marginal profit function, these three functions. So this slide is just meant to define everything and give you some background whenever you encounter financial calculations, but they tend to be the simplest form, maybe a little bit hard to set up the original equation, but the simplest to understand. So we're going to go through just one example today that has a few parts to it of our business calculus. And the extra handout that I'm going to provide might have a few more examples that relate to the marginal cost function, revenue function, and profit function. So I'm gonna bring down my slide. There we go. So a company sells 1,500 movies or DVDs, do we even have DVDs anymore, per month at $10 each. Market research has shown that sales will decrease by 125 DVDs per month for each 0.25 increase in price. Now here we're talking about movies. This can easily be used in terms of stock prices. So for example, when mathematicians or business or financial analysts are looking at the behavior of a stock and they know an article or a study has been published about market research and how demand, supply, or behavior of individuals will affect the profit margins or the ability for the company to maybe sell their products. And they can use that information to predict increases, decreases in the stock of the value of the company. So financial math and financial calculus is a fascinating topic. Determine a demand or price function. So if we let X represent the number of DVDs sold per month, P can be the price of one DVD, and N will be the number of 0.25 price increases. We can come up with two linear equations. I think we did this a lot in grade 10, right? Take problems like this and come up with linear equations to describe this particular scenario. Now, if we want to rewrite P in terms of DVDs sold per month. So let's look at this. We know that in terms of the DVDs sold per month, if the company starts off selling 1,500, let me hide this, and it will decrease by 125 DVDs per month, dependent on our P function, the price of one DVD, which is $10 each, and will increase at 0.25 N. So both of these equations share a common N value. From equation number one, if we isolate N, we can express N in terms of X. With equation number two, if we simply take that value of N and substitute it into our P function, so our price function is equal to 10 plus 0.25 of the N that we isolated from equation number one. That's our N. Now we can get rid of the denominator by obviously cross-multiplying the 0.25 with the 1.25. But when we simplify this function, we get still a linear function, 13 minus 0.002x. This is a good question to just kind of review your skills from grade 10 math. So that gives me the demand price function. This is the price for one DVD when X number of DVDs are sold. Because we took the equation for DVDs sold per month and substituted into our price function. So with that equation, the demand price function, we can figure out marginal revenue. So remember, revenue, it would make sense if X represents a number of DVDs per month and price is the price of one DVD. Well, revenue is always the number of DVDs sold by the price per DVD. So we can write that mathematically as our revenue is X times P of X. Sorry, I'm just going to put a shade on this question as well as the next two. Okay, so if I substitute my price function that we've come up with and multiply that by X, I now have a quadratic function. So revenue, we have a linear function now multiplied by the monomial X gives us a quadratic function. If I take the derivative now of my quadratic function, I am back to a linear function that represents the slope of the tangent line, or what we defined before, revenue is the marginal revenue function and refers to the instantaneous rate of change of total revenue with respect to the number of items sold. So that's how we define the derivative of our revenue function. And if we, because the question is asking when sales are 1,000 DVDs per month, if I substitute 1,000 into my marginal revenue function, I get a instantaneous rate of change of 9. So that'll be the rate of change of the total revenue with respect to the number of items sold. How can we interpret that in terms of a statement? When sales are 1,000 DVDs, the revenue is increasing at a rate of $9 per additional DVD sold. So I know we're throwing a lot at you in this particular question, but it's to illustrate that derivatives are not just equations. We can apply them to a number of different real life scenarios to come up with useful information that can drive the behavior of a company or a product or an experiment. For the next equation or next example, we're going to actually be given the cost function. Okay, so the cost of producing DVDs, we have a quadratic function for that, and it's saying to determine the marginal cost when the production is 1,000 DVDs per month. Now, from that post I did earlier, the marginal cost function refers to the instantaneous rate of change of total cost with respect to the number of items produced. So instantaneous rate of change here, we connect with our derivative function, as opposed to the average rate of change, which was what we looked at before, more similar to the formulas we learned in our functions course. So this time we don't have to come up with the cost equation. We've been given that. So we can simply go straight to the derivative. So the constant number we can ignore, and we're applying our power rule for derivatives to negative 0.4x squared, which gives me negative 0.008x. And 9.2x becomes the constant 9.2 when I apply my power law for derivatives. And after that, it's all just simply about substituting 1,000 into that equation, which gives me an answer of 1.2. So because we're talking about rate of change here, the 1.2 actually represents a cost of $1.20 for each additional DVD produced. So the cost of increasing the price for each additional DVD produced. So this is when we're producing 1,000 DVDs. If I substituted the price of increasing or producing 500 DVDs, 800 DVDs, 772 DVDs, I would just plug in that value always into my derivative of the cost function, which we define as the marginal cost function. And finally, the last question is determine the actual cost of oh, no, that's not our last question. Let's see, I think I skipped one. Oh, no, here it is. Determine the actual cost of producing the 1,000 first DVDs. So here we would take our derivative, or sorry, our cost function, and we would simply subtract when I plug in 1001 versus when I plug in 1000 into the formula. So very straightforward calculation. It's just a difference calculation. And this is more similar to something we would have done in the regular calculus course as opposed to this course. So I'm just including it here as an example, as something interesting, but it won't be on this particular test. So it just goes to explore the marginal cost a little bit, the idea of marginal cost. Now, if I wanted to determine the profit and marginal profit for monthly sales, profit and marginal profit, that would be equivalent of taking my revenue function and subtracting my cost function. So that would give us our profit function. So my revenue function we've determined before. The cost function we were given. Both were quadratic equations. So when you subtract those two quadratic equations, you still have a final quadratic equation. So you're never going to be given the profit function. You would always be asked to solve for it by taking revenue minus cost. And to find the profit of the monthly sales, we would simply plug in 1,000 DVDs into the profit function to get a value of the profit for monthly sales of 1,000 DVDs. Now, we wouldn't stop there, because here we know that, sorry, let me stop recording. Oh, Angela. Sorry. Okay, so the profit of 1,000 DVDs are sold. When the profit is sold, we have, when 1,000 DVDs are sold, we have a profit of $800. Now, the marginal profit refers to the instantaneous rate of change of the total profit. So the marginal profit would just be taking the derivative of my profit equation, which is simple enough, and substituting 1,000 here. But I want to really go over what this value means. So marginal profit refers to the fact that if 1,000 DVDs are sold, the profit will increase at a rate of $7.80 per additional DVD sold. So marginal profit, when companies determine their revenue and their cost for a particular month or particular year, this is where we look at optimization, or we can look at just the opportunity cost, that if we were to raise the price, what would be the potential profit? Is it worth it? Or would our profit maybe turn into negatives, which would result in a loss? If I had a negative value here, it wouldn't be a profit anymore. So these calculations can really aid companies or help companies to make essential decisions to determine the products that they wish to sell or just the behavior of their company in general.